Hi, this video is an overview of AVL trees. The previous video went over self-balancing binary search trees in general. This video goes over how AVL trees specifically work. So an AVL tree is one of these self-balancing binary search trees. It's named after the inventors Adelson Velsky and Landis, so AVL comes from the initials of the people's names that discovered this. It's a classic. The AVL tree was actually the first ever self-balancing binary search tree that was discovered, and it's still widely used in practice. A lot of map and set data structures and practical programming languages still use AVL trees. The balance invariant on an AVL tree is that the height of two siblings can differ by at most one. Two siblings are two nodes with the same parent, so they can have the same height, or their heights can be off by one, but they can't be different by more than one. And remember, for the purposes of these height calculations, a null pointer counts as a -1. We're going to claim now and prove later that this balance invariant implies that every AVL tree has logarithmic height. And it is mathematically true that if you form a binary search tree where the height of every siblings is only off by at most one, then you can only ever form a logarithmically height tree. We'll see why that is a little later. First, we're going to get into how this works. I put this here because I think an AVL tree is a classic, kind of the way that a good old-fashioned wooden doorstop is a classic. You know, this is ancient technology from thousands of years ago, but it's still one of the best ways to hold a door open. You know, it's hard to improve on this thing. So AVL tree is kind of the same thing. This was invented very early in the history of computer science and data structures, but it's proven itself. It's still widely used. It's still one of the favorites to actually implement. Let's say a little bit more about this balance invariant. So remember the definition of the height of a node X. Every leaf node has height 0. A leaf node has no children at all. And a null pointer off the bottom of a leaf or a parent with only one child counts as a -1 height. And a parent node that has one or two children has its height defined as one more than the greater of the children's heights. The balance factor of node X is a way that we can quantify how balanced a node is based on these heights. And the balance factor of node X is the absolute value of X's left child's height minus X's right child's height. So basically, look at the height of the left child, look at the height of the right child, take their difference, and treat that as a non-negative number with an absolute value. That's what these bars mean, is absolute value, so negatives become positives. The AVL balance invariant, again, is that every node's balance factor is only 0 or 1. So you're allowed to have balance factor 0, that's perfectly balanced. Balance factor 1 is okay, that's a little bit imbalanced, but balance factor 2 is over the line. So anytime a tree has a balance factor of 2 or more, that would be a balance violation, and if we want that tree to be an AVL tree, we need to fix it somehow. Let's look at how we can calculate these balance factors before we start working with them. On this slide and some of the other ones, I'm using this notation in the legend here where we draw a node, and on the left side we draw the balance factor in orange, and we write the height of that node in blue on the right. We've been working with heights for a while, so that should be familiar. What's new is the balance factors in orange on the left. So the balance factor is the height of the left subtree of a parent minus the height of the right subtree, and it's an absolute value situation. So in blue we have the heights. Every leaf has a height 0. The parent of a leaf has height 1. And for more complicated situations where a node has two children, you look at the heights of the two children and add 1 to the greater of those. So this node here has a height 1 child and a height 0 child, so its height is 2. The root node has a height 2 child and a height 1, so the root's height is 3. Let's fill in the balance factors. Every leaf node has balance factor 0 because its left child is null, its right child is null. So we have a -1 minus a -1. Those cancel out and you get 0. This node here has a balance factor of 1. Its left child is -1, its right child is 0. -1 minus 0 makes -1. The absolute value of that is 1, and that's because the heights are differing by 1 at that location. Over here we have the same situation. I've got a node on the left and nothing on the right, so balance factor is 1 in orange. This node here, the left child of the root, has a left child of height 1, a right child of height 0, so these two are siblings. Their heights are differing by 1, so that's a balance factor of 1. Finally, at the root, the left child has height 2, the right child has height 1. The difference between those is 1. These are the two sibling nodes, and their heights are differing by 1, which is allowed. Here's a couple pictures of some valid AVL trees. The one on the right is the one we just worked with. You know, it's moderately imbalanced. It's not perfectly balanced, but it's close enough to count as an AVL tree. The one on the left is a perfect binary search tree, every parent has 2 children, and therefore the balance factor is 0 everywhere. And that kind of shows that these balance factors are a pretty good measure of how balanced a tree is. When there's 0 everywhere, it's perfectly balanced. When you've got some 1s in the mix, it's a little bit imbalanced. If you have any 2s, it's pretty imbalanced. Here's an example of what some invalid trees could look like. These are not AVL trees because the balance factor is too far off. This is the smallest tree we can form that violates the invariant. A single node always, a single leaf node always has balance factor 0. That's okay. If I pile one more node on top of that, the balance factor can be up to 1. If I have a lopsided 2-node chain like that, the balance factor can be up to 1. If I stack on one more node and make a chain of 3 nodes, then the balance factor can be 2. If it's left heavy like this, where all the nodes are on the left, all the nodes are on the right. So the root node here has balance factor 2 because the left child has height 1, the right child is null, which counts as -1. 1 minus -1 makes 2, and 2 is too imbalanced to count as an AVL tree. By the way, notice that it wasn't possible to violate this invariant until we got a height 3 tree. And that's going to come into play later when we get into trinode restructuring. A height 1 subtree is always balanced. A height 2 or 2 nodes is always balanced, but when you have 3 nodes in a row, it's possible to get imbalanced. This is the symmetrical situation where we have a right-heavy tree, 3 nodes in a row. Balance factor comes out to 2 for the same reason. This example over here might be a little more realistic. This is a tree that's close. I've got some 0s and 1s mixed in that are okay, but there is one violation, so this does not count as a valid AVL tree. This node right here has balance factor of 2 because it's got a height 2 left subtree, nothing on the right subtree. This also goes to show that the balance violation is not always necessarily at the root. It could be at a different location. So let's go over how the AVL insert operation works. It follows the pattern for self-balancing binary search trees that first we do an insert like a plain binary search tree. Then we check to see if the invariant is violated, and if it is, we fix it. We call this a search and repair approach. So first to just do plain old-fashioned binary search tree insert like we've been learning about. That adds a leaf node, and look for a possible balance invariant violation. If we find it, we fix it. It's actually true that inserting can only imbalance one node, so we only have to look for one violation, and if we find that one violation, fix it. Here's what the pseudocode for the whole thing could look like. We do the plain binary search tree insert to insert a leaf at the bottom. Update the heights and balance factors on the path from the new child to the root. So let's say I inserted a new node right here. Well, that increases the height of the parent, or it may, and that might increase the height of that parent, that might increase the height of that parent. So the nodes on the path from where I put the new node all the way up to the root need to get their heights updated. And similarly, we need to update the balance factors. None of the other nodes could have their height or balance factor adjusted, so we don't need to bother with those. But the nodes on the path up to the root need to have their heights and balance factors updated. And then if we notice that there's a node anywhere that has a balance factor of 2 now, that's the invariant violation we caused, and we do this trinode restructuring operation at that node that fixes the balance. And we'll go into that in a separate video, how that works. Erase is basically the same idea. We do the same search and repair thing. So do the erase operation like a normal plain binary search tree, the whole thing of finding the node to erase. And if it has 0 or 1 children, you just cut it out. But if it has 2 children, you replace it with the in-order successor. All of that stuff happens as normal. And then we update all of the heights and balance factors on the path from the node that we removed up to the root. And this time we actually have to look for multiple nodes to rebalance. The erase operation, unfortunately, could imbalance more than just one node. So erase is a little bit more complicated because you have to look at every node on the path from where we made changes up to the root and say if it's imbalanced, do a trinode restructuring to fix the balance, and then keep going. With insert, you looked for one imbalance and fixed it, and you're done. With erase, it has to be a loop of look for the first imbalance, fix it, and then keep looking in case there's more. When you get to the root, you're done. So that's how AVL trees work in general. We're going to get into some more details in the next videos.